Today I'm going over how to write production code in Python. This is a topic that's extremely important that many developers honestly never learn, and it's the number one thing that separates a junior developer from a senior developer. If you're serious about writing Python code and becoming a Python developer, then definitely watch this video, and I'm going to go over a lot of concepts with in-depth examples so you can understand exactly how you can apply them to your own codebase. Okay, let's dive into it. And by the way, if you want access to all of the code that I show in this video, as well as this cheat sheet that I have on screen right now, you can do that by clicking the link in the description. Simply sign up for my newsletter and I will send it over to you for free. So this video will cover 8 main design principles with in-depth examples. We'll quickly go over what those principles are, and then we'll dive into the code and explain them more in depth. Number 1, cohesion and single responsibility, encapsulation and abstraction, loose coupling and modularity, reusability and extensibility, portability, defensibility, maintainability and testability, and then simplicity. Now, there are many other design principles, and this is not an exhaustive list, but these, in my opinion, are the most important and the ones that you definitely need to get right, especially if you want to get to that senior level. So with that said, let's dive in and start talking about cohesion and the single responsibility pattern. Now, this essentially states that you want to have one job for every single piece of code that you write. So in the case of Python, every class or every function should only have one reason to change. Now, when you have high cohesion, that means that related things are grouped together. Related classes are in the same file. Related modules are in the same folder. Related code is in the same function. So you want to always aim for a high cohesion when you're writing code. Now, single responsibility principle is just something that states that every piece of code that you write should have one single responsibility. And this actually ties into a lot of the other design principles that we'll talk about and will allow you to just generally have significantly better code. So let's start by looking at an example of bad user management. Full disclosure, a lot of this code was generated with AI, but obviously I reviewed it and told it what to generate just faster than me writing it from scratch. So here you're going to see an example of a class that at first glance looks fine. However, as a program grows, which is really the importance of these design principles, scaling and getting into large enterprise-grade software, this becomes a really big problem. So if we skim through this, you'll see that we have a user manager class, and inside of here, we initialize it by creating some users, and then we have kind of this mega function that does a bunch of different things. It performs validation, it looks in the database, it sends an email, it then reports this to some logs, and all of the tasks like sending a welcome email, logging the creation and generating the user report are all inside of this one class, which is called the user manager. Now, again, in smaller programs, this is fine. No one's going to yell at you for this. But as things get larger and more complex, and as you maybe want to change the database or change the email reporting system or change the logic here, right, for the logging, it can be very difficult to do that because you've tightly coupled all of these operations together. So let's have a look at some good user management and see how we separate this out. Now, at first glance, when you see these examples, it's going to seem overkill. It's going to seem like, why am I doing this? It's so much more code. But again, this is that systems level thinking that you have as a senior software engineer, where you're anticipating what's going to happen in the future and preparing for that now. So in this example, every class that we look at has a single responsibility. We have a class for an email validator, for a password validator. We have a user repository class, and notice that while it seems simple, right, and we just have single functions inside of here, it's very clear what each of these classes are doing. For example, this is how we save a user. This is how we get all the users. This is how we initialize the users, and it's stored in a very accurately named class, user repository. Continuing, we have an email service. In here, we could easily change the implementation of this function or use some other email service. We have a user activity logger, and then we go to our main user service. In here, our function effectively does the exact same thing that it did before, but now we delegate all of this work out to the individual services, where if we did need to change something in the future or debug our code, or maybe even change the service, it's a lot easier to do that, right? So when we initialize the class, we take in a repository, we take in an email service, and we take in a logger, and we then use that inside of the class. Okay, and then if we keep going, you can see that now if I wanted to change how the user service operates, it would be very easy for me to do that. I would simply just change the repository that I passed to my user service, right? Or I would change the email service or change the logger because of the way that I've set this up. Now, as you can see, some benefits, right? Each class has one reason to change, easy to test validators, so you can test all of these individual functions. You can easily swap the various services, and you can reuse these components in other contexts because they're not tightly coupled into this one kind of user mega class that we had before. Now, again, in small programs, this isn't an issue. In fact, you're probably looking at this and going, this is completely overkill. Why would I ever write this? Again, this is only important in large systems, which is what I'm trying to teach you in this video. You may not start with this type of code, but as your software gets more complex, you want to start thinking about these things and make sure that you're really just doing one thing in all of your classes and all of your functions, and that the cohesion is good. Now, before we get into the next design principle, I want to take a moment to thank today's sponsor, Boot.Dev. It's an online learning platform designed specifically for back-end development, and it approaches learning in a way that's far more interactive than the usual video-based courses. Rather than having you sit through hours of lectures, Boot.Dev puts you straight into hands-on coding. You'll work directly in your browser, building real projects while learning back-end fundamentals like APIs, databases, and server-side logic using Python and Go. Now, what makes it stand out is the way that it borrows from game design. You'll progress through levels, unlock new content, and keep your momentum up as you go. The platform is filled with exercises and practical challenges, so you'll end up writing a lot of code, which is exactly what helps you improve. Now, all of the core content is free to access, and if you decide to commit to the annual plan, you can use the code TECHWITHTIM to get 25% off your first year. I've been going through it myself lately, and honestly, it's surprisingly addictive. Thanks to Boot.Dev, now let's get back into it. Now we move on to the next topic here, which is encapsulation and abstraction. Now this essentially means that you want to hide the implementation details from other users or other programmers in our case, and simply present a useful interface. What that means is that you want to keep internal state private, you want to expose the behavior of the code, not the data, and you want to use things like properties and getters for controlled access, and always abstract away all of the complexity. Now this can get out of control quite quickly, but let me show you what I mean, because this is something that a lot of developers get wrong. Okay, so we're having a look at a pretty simple class here, right? A bank account class where we define some owner, we have some balance, and then we define some transactions. Now, it seems like what could possibly be wrong with this code, right? There's hardly any code here at all. But the thing is that with this type of code, it's actually too flexible. It allows us to do pretty much anything, and while we may know how to use this class correctly, another developer or someone implementing this bank account, right, or wanting to use it in their program may not. So you can see that we can, for example, have a negative balance, right? We can have some, massive value in the balance that maybe doesn't make any sense. We can corrupt the internal state by setting it to something that's, not a list, right? And you just notice that we have all of these problems where, again, if we're just writing this code for ourselves, it's not an issue. But if we wanted to provide this bank account to someone else to use, they can mess it up very badly, right? And this is going to tie into a lot of the other design principles that we'll look at later. The point is, when you design things like a class that you intend for other people to use in the future, you want to design it so that it works exactly the way that it should work, and you protect against all of these weird edge cases like negative balances, right? And, corrupting the internal state. So what I'm going to show you again is going to look overkill. There's always a debate on when to do this, but I want you to understand these patterns because that's the point of this video. So if we scroll down, notice that now my bank account class, first of all, is expanded. It has a lot more code, but now it is very kind of secure in terms of the way in which we utilize it, and it exposes behavior, not data. So notice that we've used what's called a private attribute in Python. This is not actually truly private, you still can access it, but by using a leading underscore before an attribute name, that indicates that this is internal to the class or to the structure, and that you should not modify it from outside. So now, after the bank account is initialized, the owner, the balance, and the transactions are all private attributes that we should not touch outside of using the interface that's exposed to us, which is the methods that are here, right? The public methods. So you see, we go down here, we have a deposit method. Now in the deposit method, we have value errors that we're raising, where you can't deposit a negative amount, right? And then we modify the internal state. We actually create a transaction, so we're now tracking all of this internally in the way in which we should do that, and we're not exposing all of this kind of data and functionality and implementation that we don't need to. If a user wants to deposit money in the bank account, again, like another programmer using this class, they simply use the deposit method. They don't need to worry about how it works. Same thing with withdrawing, right? We make sure they can withdraw the correct amount. We make sure that it's, a amount that's non-negative, right? We then adjust the balance, we put the transaction in here, and everything is done properly. Then we have a get balance function, which actually exposes the internal state. Here, we could also maybe do something with the balance, like rounding the value or something. We can generate a statement, and then we have private internal helper methods, which we denote again with this leading underscore, which are only meant to be used internally and not exposed to the user. So as someone using this class, all you need to know is that you have these 4 methods, you can use them, they simply work, and all of the implementation details are hidden from you. Now the next example that we look at here is called loose coupling and modularity. Now, the definition of coupling is how tightly things are connected together. Typically, when you write code, you don't want to couple things together too much. What that means is that you don't want to write functions that rely on other functions or rely on some specific implementation or some specific class or environment variable or all of these things that are essentially tying all of these components in together. You want to make things as flexible as possible and to purely rely on kind of their internal state and logic as opposed to external things, right? I know it's kind of a vague definition. But here, what we're going to do, right, is we're going to talk about interfaces, abstract classes, injecting dependencies, and components that can be swappable. So rather than coupling, for example, our email service to only one email provider, it should work with any email provider. So we could simply swap that in the future and we're good to go. And that's exactly the example that I'm going to look at right now with you. So let's have a look at some tightly coupled code. So we have this email sender class, right? And notice that directly inside of my order processor, I actually couple the email sender inside of it. Now, the reason why this is coupled is because now if this email sender class ceases to exist, this code no longer works, right? And it means that I now cannot change the email sender class that I'm going to use inside of here. I would have to actually just make a modification directly to this class. Instead, what you would want to do is you would want to take in the email sender as a parameter, and rather than relying on an exact class implementation, you rely on what's called an abstract class, which actually enforces or, kind of defines an interface that any email sender needs to have. We'll talk about that more later, but that's a quick example. So the point is we've coupled this together, and now anytime I want to send an email, I have to use this email sender. So let's have a look at a loosely coupled application, which is again going to look overkill, which is this good notification folder. Now inside of here, we have a lot of code. So let me just open it up and I can show you how we've decoupled this application and the fact that now all of these components are individual and we inject them when we need them. So inside of main, for example, what we can do is, create an instance of an email notifier. We can create an order processor by passing that email notifier inside. For our order processor, we also could pass an SMS notifier, right? We also could have a multiple notifier where now we pass in an email notifier or an SMS notifier, and now this works. So this is just an example of usage, how now my order processor isn't coupled to one type of service, it can actually use multiple. Now the reason why that's the case is because we've defined what's called an abstract base class. In Python, this is kind of the closest thing you can get to what's referred to as an interface, where essentially you can define a class that dictates what any class that inherits from it must define. So in this case, we're going to say anything that can be used as a notifier must have this send method. The send method has to look like this, where we have a recipient, a subject, and a message. Now, by writing this method with the abstract method decorator, this enforces that anything that inherits from it that wants to implement this class must have this method. So now, if I go to my order processor, you'll notice that for my order processor, I actually only rely on the fact that I'm using a notifier. So I say, okay, I'm going to import this notifier class, and I'm going to use a notifier as my parameter type, which means you can pass me any concrete implementation of the notifier. I don't care what it is, so long as it has this definition, right? So long as it has this send method. So now inside of here, I can use the send method, and it doesn't really matter what implementation of the notifier that I'm using, this class still works, and it's loosely coupled from what's actually notifying the user, right? So now if I go to my SMS notifier, you can see I inherit from this notifier abstract class, and I can implement my SMS sending, right? If I go to my email notifier, same thing, I inherit from my abstract notifier, I implement the send method, and now both my email notifier and my SMS notifier can be used interchangeably inside of my order processor or anywhere where I want to rely on this notifier abstract class. Same thing with the multi-notifier, I take a list of notifier objects, right? And as long as they have that implementation and they have that send method, I'm good to go. This allows me to use them interchangeably and is a huge benefit. Now, the next pattern on my list is reusability and extensibility. Essentially, this means ask yourself the question, can I add new functionality without editing existing code? Sounds straightforward. Let's have a look at an example. So here's a bad example of a report generator. We have this monolithic generator where it's very difficult to extend it and add functionality because we do everything inside of this one function. Right? So we check, if there's a text format, if there's a CSV format, if there's an HTML format, and if I wanted to add additional formats, I would need to go in here, I would need to understand the logic, I would need to write another elif statement, and I would just keep doing that and have this kind of endless nest of if-elif statements, which really is not best practice. Again, for short programs, fine, not an issue. For larger software, starts to become a problem and really isn't good practice. Now, let's hop over to the good report example and see how we can modify this. So similarly to what we looked at before, we now define an abstract base class. This defines that anything that wants to be a report formatter must have this format method. We then are able to write all of the different format methods that we need. So we can have a text formatter, we can have a CSV formatter. Notice they're all implementing their own format method, and they can have other ones if they want to. HTML formatter, now I have a new JSON formatter, now I have a new Markdown formatter, right? So I've written all of these individual formatters based on this interface right here. And then for my report generator, what I can do is I can take in any report formatter, right? And then I can generate a report by simply using that formatter. So now if I want to extend this, there's no changes that need to be made to my report generator. I simply write another report formatter, and I can now pass that into my report generator, and it can generate a report. It's extensible without needing to be modified. And if I go down here, you can see that I can use this generator with all these different formatters. I can even use a list, for example, and it just works. Now, the next design pattern on my list is frequently forgotten, and that is portability. Essentially what that means is what I'm writing right now going to work in a different environment? Is it going to work if I don't have the newest version of C++ installed? Is it going to work if I'm not on Windows 11.2.1? Is it going to work if I'm not on this new Mac version or using this crazy software, right? So when you think about portability, you essentially want to think, okay, how can I make sure the code that I'm writing is as portable as possible and is going to work in as many situations as it possibly can? Okay, so let's have a look at some examples here by looking at a file handler, which is actually where I most commonly see this done wrong. All right, so let's look at a bad file handler. Notice that we have this data processor, okay, and then inside of here, we hard code some input and output directories. Now, immediately by us hard coding these directories, what we've done is just ensure that this code will never work on any machine other than ours. The reason for that is that I would need to manually change this, which is obviously not good for the code. That doesn't make it portable. And this is a Windows file path, which means even if we did have these exact directory structures on Mac or Linux, for example, this would simply not work because of the fact that we've hard-coded the Windows style path rather than using a dynamic path, which you can do in Python. We've also hard-coded a database connection. We've hard-coded the API endpoint. So again, I can only use this in this exact environment situation, which is almost never when I would want to use this, especially in production. Okay, and then same thing for processing the file, right? I'm building these hard-coded paths with this Windows style separator, and this only now will work on Windows. So if we go to a good example here, you can see that what I do right away is I import OS and I create this environment variable file. Inside of here, I put all of the dynamic values that I may need to change depending on the environment in which I'm running this code. Very common, you've probably seen an environment variable file before, right? I have my database information, I have my API information, I have the current environment I'm in, I have the file path directory which works cross-platform, right? And now if I go here, I rely on environment variables rather than relying on hard-coded values. Same thing for my file paths. I use the path variable from the path lib, which makes this dynamic and works cross-platform. Okay, there's a lot of other stuff in this example. The point is, this now works no matter what environment you're in, because we've created this kind of dynamic environment variable file that we read from, which tells us essentially what to do and what values to use based on our environment. The next example on my list is defensibility. Now, this means writing your code as if an idiot was going to use it. That essentially means that you want to validate all of the input. You want to have, for example, least privilege access, which we'll talk about later, and things like safe default values. Now, you always want to ask yourself, what's the worst thing that could possibly happen to my code if bad input was provided? And you want to make sure that you defend against that situation. You're essentially writing code that no other developer could use in a way where it would, alter the system or mess something up quite badly. So let's have a look at some examples here so you can see what I mean. And let's get into it. Okay, so here's an example of a bad payment processor. You can see that we have, debug mode is equal to true. Probably wouldn't want that to be true. We'd probably want that to be false, because if someone accidentally left that on, that could be a huge issue. For maximum retries, we probably don't want that to be 100. That's a crazy default value that could potentially cause the system to lag or even crash. And then we don't have any timeout value, right? So all these default values that we've set are not safe. Whenever you set a default value, you want to set it in a way such that if someone didn't change it, your code would work properly and it would be a reasonable value, right? Now, same thing with processing the payment. The biggest thing you can make a mistake with is not validating or sanitizing your input. So in this case, you can see that we have some amount, some account number, some CVV, and it's not even typed properly, right? So we don't even have like the type hints in Python. And this means that someone could pass, a string for an amount. They could pass an invalid account number. You get the idea. And here we're not checking any of those things. Okay, so that's kind of the idea, is that I can use this function in crazy ways that will cause a crash or an exception in my program, especially if I pass something that, just isn't the right value. I also could pass some massive amount or, the wrong account number. You get the idea. This function is prone to be used incorrectly. Now, if we go to a good payment example, you can see that, again, it looks more complex, but this is what you need to think about. We have custom errors, so validation errors and payment errors. We have a payment result, which is a immutable type, which we define with a data class. We have a payment validator, where we validate that an amount is actually correct before we allow you to charge that amount. We validate the account to ensure the account is correct and accurate, and that the account number is clean before we actually try to use that. We validate the CVV number, again, if you're talking about like a credit card payment. And then we go through our payment processor. We have nice, clean, safe default values, right, for the processing of the payment. We make sure that everything is valid before we start trying to do anything. We only log the necessary information. We never log sensitive data. And then when we try to process the payment, if it doesn't work, we throw an error that makes sense so the user knows what the problem is. We then create an immutable result, which means you cannot modify the result, which is best practice, so someone doesn't accidentally change one of these values, which we shouldn't change, related to a payment. Hopefully you're getting the idea here, but we've defended this method and this code really well, where now someone can't really use this incorrectly. They can just call the function, and even if they pass the wrong values, they're going to get clear error messages on what's going wrong, and we're going to make sure we don't accidentally charge someone's card with some ridiculous value. Now we move on to the next example, which is maintainability and testability. The thing that many people fail to realize about software is that the most expensive thing about it is not writing it, it is maintaining it. Any software that you write, no matter how large, is something that is prone to errors, prone to bugs, and that could eventually need to be changed, fixed, modified. Who knows, right? Some developer could mess up their operating system, which could cause all of your software to go down and force you to have to go in there and make some changes. So when you're writing software, you need to think about how you're going to maintain it, and more importantly, how you're going to test it. Especially as software scales, you need to have automated testing for this software. You can't rely on someone manually testing every single feature, and even if you could, a lot of stuff is going to slip through the cracks, right? So what we're going to do is just quickly have a look at an example of how you write maintainable and testable code, focusing a little bit more on the testability side, because code that is testable is kind of by default more maintainable. Not always, but in most cases it is. All right, so let's have a look at an example of a bad calculator. Now, this is a calculator that has a super complex calculate method, right? We have all these kind of nested statements. We're dealing with tries and excepts and with statements, and we're writing stuff to a file. We have all these side effects that are happening inside of our function, and we're just doing like so much stuff that at first glance, it's very difficult for us to understand what this function does. And if I wanted to test it, there's like 30 different examples of things that could happen in this function, right? I pass some expression, it could maybe be a plus, it could be a minus, it could be a multiplier, it could write to a function, it could not write to a function, it could throw an error. How the heck am I going to test this function, right? I'm going to have to think through 500 different edge cases. There's no way I'm going to get 100% coverage of this. So how do we make that better? Well, we go to this example. Notice here, I now start separating things into smaller components, like we talked about earlier, that are easier for me to test. I have a calculation result. Easy for me to check if the calculation result is correct. I have an operation parser. Rather than just passing a whole expression, I now pass an expression to one function, and this function is purely responsible for parsing the expression. That's a lot easier for me to test, right, than a whole calculator function. I have different operations. I can test to make sure my add, my subtract, my multiply, and my divide are working properly. Super easy for me to test that code. Then I have something that gets the operation. Again, I can make sure that it's mapping to the correct values. Then I have my calculator, and look at how much simpler this function is. I have A, an operator, a B, I get the operation, I perform the operation, and boom, I can test this, and it doesn't take a million different edge cases, right? And if we go to a calculator with history, same thing. We now have the ability to kind of log the history of the calculator results. Much easier for me to test how this is working, where I've decoupled it from the calculator, and I'm able to actually just make sure the component that I'm looking for, which is a history component, is working without testing the calculator at the same time. Hopefully you get the idea. Again, it seems more complex. It takes more time up front. Good code is difficult to write. That's why we have senior developers. People still get paid a massive amount of money. And I guarantee you, if you ask AI to generate this style of code, it's not always going to make the best decisions. And you need to know deep down what the correct architecture and design is, which is why I'm showing you these patterns. Now, the last pattern that I'm just going to go over verbally here, I'm not going to dive into the code, is simplicity and a few of these kind of sub patterns like keep it simple, stupid, don't repeat yourself, and you aren't going to need it. Now, these are very common patterns, so I'm not going to spend too much time covering them, but these are things that you always want to ask yourself when you're writing code. First of all, keep it simple, stupid. The simpler the code is, first of all, the harder it is to actually write. It's much more difficult to write simple code than it is to write complex code. So keep that in mind if you have an ego about writing something that's really complicated and convoluted. But it makes it just easier for you and other people to understand. You always want to simplify everything you do as much as humanly possible so that anyone in the future could get in there and modify the code. And more importantly, you can modify the code when you forget what the heck you did 3 years later. Next, don't repeat yourself. It's very common for people to redefine the same variables, redefine the same config, keep using the same function in slightly different variations across their code, and you end up with this absolute mess where there's all these different places where you might need to make a change in the future. You want to make sure you're not repeating yourself, you're writing reusable functions, that anything you're doing more than one time, you wrap it into some type of reusable component so you can simply pull it in. All of the code is contained in one place. It's easier to test, it's easier to maintain, and it's easier to change. Lastly, you aren't gonna need it. Now, this just means that you don't want to overcomplicate things at the beginning. As much as these design patterns are great, you don't always need to dive into doing these immediately. Sometimes you don't need the most extensible, flexible, testable code in the world, and if that's the case, don't add it. Don't add features that you don't actually need. Don't over-engineer solutions unless it's something that you think is actually feasible to come up in the future. For example, when I was coding my startup, I actually ignored a lot of these design patterns because I didn't need it. It didn't make sense for what I was building. It was going to take me so much more time compared to just getting out a quick prototype so I could validate the idea. So always ask yourself, what is the business need before you go into the engineering? Because a lot of us as engineers, we forget that the whole value of code is typically to generate money or value, right, for a company. So if you don't need all of those things, if it's not going to be required in the future, you don't need to go ahead and do that over engineering and spend a massive amount of time building something that just never is going to see the light of day. Okay, so that's kind of the common stuff I wanted to go over. Now, again, if you want this whole document, so this as well as all of the code and all of the examples that I have here, then simply sign up for my newsletter from the link in the description. If you guys like these more advanced, complicated videos, please let me know and I will make more. And I look forward to seeing you in another one.